In this video, we'll discuss the idea of Riemann sum. Here are the main points to be addressed in the video. Riemann sums are tools for calculating the accumulation of a function over an interval. To construct a Riemann sum, treat each interval as having a constant rate of accumulation. The accumulation for each interval is the constant rate x change in, for example, position. Add up amounts from each interval to approximate the total accumulation. You could use the rate at the beginning or end of each interval. Sigma notation allows us to represent the sum. So let's look at the idea of how to find an amount of accumulation using the scenario of a Mars rover. The Opportunity rover landed on Mars in 2004 and has been actively exploring the planet ever since. It is powered up by solar cells. As a rover travels across the Martian surface, it kicks up dust, which accumulates on its solar cells. The amount of dust that kicks up depends on the composition of the surface it travels over. A rockier surface kicks up less dust than a sandy surface. When planning a path for the rover to follow, scientists need to know how far it might travel before too much dust accumulates on its solar panels. They have mapped out a 100 kilometers path over the rover to follow and have collected satellite data about the composition of the Martian surface at various points along the route. The goal for the scientists to figure out how much dust accumulates on the rover's solar panels. The first step in figuring out the total amount of dust that will accumulate is to identify composition of Martian surface at various points along the route. Here's the table, shows the composition of the Martian surface at 6 points along the rover's proposed route. Let's straighten out that path and show the rover on the path. And here's NASA's estimate of how much dust would accumulate on the solar cells per kilometers traveled for each type of surface composition. So based on this, how can we figure out how much dust will accumulate across the rover's entire trip? It might be tempting to just multiply the numbers in the bottom row, 100 kilometers by 1 milligram per kilometer. However, if you did this, then you'd be assuming that rover traveled the entire 100 kilometers over a very rocky surface, which is not the case. So, how can we approach this problem? The first thing to do is to break the path down into distant intervals. First, we'll label path with a position from the start, and then we'll make space to record length of each distance interval. Each of the interval has length of 20 kilometers. Let's put this in the table. Next, let's make some space to compute the amount of dust we accumulate in each of these distance interval. The next thing we need to do is to recognize that the data we have are rates. For example, this 1.5 means that when the rover is 80 kilometers along its path, the dust is accumulating on the rover at a rate of 1.5 milligrams per kilometer. So at that point, for each additional kilometer the rover travels, it will accumulate 1.5 milligrams of dust. Now, as the rover travels from 80 to 100 kilometers, the composition of Martian surface changes from moderately to very rocky. And we do not know how quickly this change happens. Consequently, we can't find the exact amount of dust that accumulates over this interval. The best thing we can do is to approximate the total amount of dust that accumulates on the solar panels. To do this, we need to assume that each of these rates is constant over the corresponding 20-kilometer interval. Then, that will mean that to find the amount of dust that accumulates for each interval, we will multiply the change in position over that interval by rate of accumulation. For example, over the interval from 80 to 100 kilometers, the rover travels 20 kilometers. If we're assuming that dust accumulates at a rate of 1.5 milligram per kilometer for the entire 20-kilometer interval, then the rover would have accumulated 30 milligrams of dust over that interval. We could do this for each of the intervals. So if we start over at the beginning of the rover's trip, as the rover travels over the first interval, you'll be traveling 20 kilometers with an accumulation rate of 6 milligrams per kilometer. We multiply these to get 120 milligrams of dust accumulating. Then the rover will travel over next interval, so it will travel another 20 kilometers, multiplied by a rate of 3.5 milligrams per kilometer to get 70 milligrams of dust accumulating. Then over the next interval, we'll multiply 20 kilometers, change in position by a rate of 2.5 milligrams per kilometer to get 15 milligrams. And then over the next interval, we'll get 40 milligrams. And over the final interval, we'll get 30 milligrams. And if we add all this up, we'll get total of 310 milligrams of dust that have accumulated on the rover. Now, it's important to keep in mind that we've been making a big assumption. Since we're assuming that each rate was constant over the corresponding 20-kilometer interval, our answer of 310 milligram is not necessarily the actual amount of the accumulated dust. Rather, it's an approximation of the total amount of dust that has been accumulated in solar cells. One thing you might have noticed is that we were always using the rate of dust accumulation at the beginning of each interval. For example, at the interval from 80 to 100 kilometer, we use a rate of 1.5 milligram per kilometer for the entire interval. However, by doing this, we were assuming that the rate of accumulation remained 1.5 milligrams per kilometers over the entire interval. We can see that the rate of accumulation had dropped to 1 milligram per kilometer by end of the interval. So we could also have done the entire calculation by using the rate at the end of each interval instead of the beginning. This would have given a slightly different approximation of the total amount of dust that accumulates on the rover. This estimate, using the rate at end of each interval, would not necessarily be the more or less accurate than the one we got using the rates from the beginning of each interval. Now, to summarize our general method, to make an estimation of the total amount of quantity that has been accumulated, we treat each interval as having constant rate of dust accumulation. In this example, we always use the rate at the beginning of each interval, but we could also have used the rate from the end of each interval. Then, we find the amount of accumulation over the interval by multiplying constant rate times change in position. Then, we add up the amounts from each interval to get the approximation of the total amount of the dust that has been accumulated.